morning. So, last time we were talking about zeolite and framework of the zeolite, structure of the zeolite and effect of silica to alumina ratio on the composition or zeolite properties. Let us look at some synthesis aspects of the zeolite also. So, today I will talk on zeolite synthesis, but before that some continuation of the last lecture where I was talking the formation of the pentacell zeolite, right. So, these are 5 membered rings and secondary building block, and then these are attached to the framework. So, different say 5 membered rings which is a pentacell structure which is connected. So, basically when you look at this structure, the cage opening that has 10 rings here in terms of 10 membered oxygen rings, right. But the orientation of that crystalline phase which I was talking yesterday, it can be with the square opening, it can be with hexagonal opening, and this is what a kind of pentacell zeolite. So, which has a pore opening of roughly 0.56 nanometer. So, these are different kind of zeolites, and you can have accordingly this side diameter, channel diameter and the horizontal channel diameter, and that depends on the framework of the zeolite crystal. So, this is what the framework has been shown here. So, horizontal and the vertical. So, the channels roughly if you look at here, the linear channels have diameter of 5.1 by 5.6. So, that is the cage opening of the zeolite. Based on that the pentacell structure, right, the SBA secondary building unit, and which has now condensed polymer, and then the further condensation and you get a cage type structure. So, here and if you look at vertical zigzag channels, right, which are arranged particularly to this, and they have roughly the cage opening of 5.4 by 5.6 angstrom. So, it means depending upon these are interconnected channels now, interconnected pores in the zeolite, and that gives them a very complex geometry of the pore, right, and that is helpful in certain kind of chemical reactions. So, depending upon this the framework or primary building units, secondary building units, right, or silicon to alumina in the framework, you have different kind of zeolites and different types of the pore structure and opening. So, zeolite Y, which is a phosphorite type. So, large pore zeolite, basically larger pore size, right, 0.74 nanometer and 12 rings. So, number of more the number of rings, the cage opening will be more, right, TOT atoms which I am talking. Pentacell zeolite ZSM5 category, right, opening roughly between 0.55 into 0.56. So, horizontal and vertical structure of that, and 10 ring ellipsoid type, right. Zeolite A has the pore diameter of 0.41 nanometer, 4.1 angstrom, 8 rings in the structure, right, cage structure. Sodalite cage, it has pore diameter 0.26. So, comes in the category of microporous or mesoporous material, right, and 4 rings. So, as I said that basically silicon, aluminum and oxygen is in the ring. So, SiOAl and structure builds like this something, right, here again oxygens are connected to the framework and this structure builds. Sometimes this silicon can be, this is Si4 plus can be replaced by phosphorus 5 plus, right, which does not give the acidity to the zeolite, right, rather it can be a kind of neutral zeolite or mild acidic zeolite, right, it depends on the amount of this phosphorus. So, we can have different categories. So, this what I said earlier also TOT, where T is either silicon, aluminum or phosphorus also, right. So, then it can be a either aluminophosphate zeolite, AlPO4 sometime like this, or also we called SAPO, silico aluminophosphate, right. So, there can be silicon, there can be aluminum and phosphorus, or all the silicon can be replaced from the framework by phosphorus 5, and that will again you will have a kind of aluminophosphate type of zeolite, right. So, these zeolites have mild acidity. So, for reaction something like methane conversion to olefin hydrocarbons. So, SAPO can be used, right. So, because stronger acid sites may give more coke on the catalyst. So here the ALOP, so aluminophosphate type zeolite, right, or in some cases if you just replace again the phosphorus by silicon, you can have a SAPO type zeolites also. So, the weaker acids compared to the zeolite and AlPO4 type moleculosives, they are generally neutral and do not have any exchangeable ion 5 plus, right. So, the pore structure, so again you can see here the phosphorus, oxygen, aluminum, then again oxygen, phosphorus and aluminum, right, so on. So, this structure builds up, so which can be something like this roughly 7.3 angstrom of pore opening, right. So, different kind of frameworks of this aluminophosphate zeolites can also be made by this. So, this is again a type of SAPO zeolite, right, where the Virginia Petroleum Institute, and this is 12 angstrom, and in the that is the pore opening of the zeolite, and number of rings can be calculated 1, 2, 3, 4, 5, 6 something like that, right. So, different kind of silico aluminophosphate zeolites can be formed depending upon the silicon to aluminum ratio and the phosphorus introduced into the framework of the zeolite. So, as I discussed last time, there can be different kind of structures of the zeolite. So, you have LTA 4.1 angstrom, that is one kind of zeolite, then that is LTL type 7.7 angstrom pore opening, and the type of 12 membered ring, this is 8 member ring 12. So, diameter cage opening is increasing. This is a 2D structure type, so 6.6 by 6.7, so 12 membered ring, right. Again this is a GIS 4.5 by 3.1. So, 2D 3D cage structures can be formed, right. So, 1D channel or 3D channel. So, there can be a 3D structure in the form of zeolite material. So, different depending upon the oxygen content, the different oxygen membered ring can be associated to the zeolite depending upon the silica to alumina ratio in the zeolite and the structure of the primary building unit. This is again another category of mesoporous material, right, MCM microcrystalline or mesoporous materials, and there again you have the different kind of say 3D structure. This is just a kind of 1D structure and a lamellar structure, right, slit type structure like clay material, right. So, different kind of these microcrystalline materials can be made by selecting the silicon, aluminum and the preparation condition. So, they have very specific properties in terms of the catalytic activity, right. So, generally they can be only silica also with large amount of silica also highly acidic in nature, right. So, the different type of MCM materials can be prepared. So, MCM 22, MCM 41, so with high silica to aluminum ratio. So, they have certain importance like this MCM 48, you see it is a 3D type of structure, right, and this is just MCM 41 which has just a laminar or 2D or laminar structure, right, 1D different kind of channels can be here. So, the important thing is that the MCM 48 is more resistant to pore blockage, right, because depending upon the cage openings, right, and the acidity of that catalyst. They have high surface area, high pore volume, and they have good thermal stability, because stability of zeolite is one of the important issue, right. At high temperature they do not sustain their structure collapse, right, when you have high temperature, because the framework that collapse at higher temperature, right. And higher catalytic activity than 1D which is your MCM 41. So, MCM 48 which is a 3D type structure has certain properties in terms of the catalytic reaction. So, they are better. So, because of this 3D it refines the accessibility of molecules, what I was talking the shape selectivity, right. So, they are shape selective. So, accessibility of the molecules inside the pore geometry of the zeolite by imparting the fixed window opening. So, they have very definite window size and thus limits the diffusion of molecule within kinetic diameter larger than this window. So, a larger molecule whose kinetic diameter is larger than the pore diameter or pore opening, it cannot go into the pore of a zeolite. So, it becomes a shape selective. So, all the time when we talk a zeolite material, the pore opening becomes important, because the controlling parameter is the diameter or size of the pore, because these are microporous mesoporous material, right, and that is to be compared with the kinetic diameter of the reactant species, right, or also the product species. Then you can have the idea about the product selectivity. So, one can take a definite kind of pore openings or prepare a definite kind of zeolite material, right, or molecular sieve material depending upon the kinetic diameter of the reactant. So, especially when you look like methane conversion to higher hydrocarbons or hydroisomerization reactions like in the of these larger molecular weight paraffins, right, and you need to isomerize them for the diesel range of hydrocarbon or gasoline range of hydrocarbon, and when you have Fischer-Tropsch reaction, then you get a series of products. So, this product needs upgradation. So, hydroisomerization required, and when you do that, you need to find a definite kind of pore structure, pore geometry along with the acidity, right. So, diffusion and the kinetic is very important in this kind of definite pores, right. So, it may not allow the larger molecule. So, reaction is not possible if the pore size is too small, right. So, that is also important. So, you have to just look at this allows the safe selective entrance of the molecule. Activity of such molecule is often hindered. So, if the molecules are larger or kinetic diameter of the reactant species is larger, it may not diffuse into the pores of the zeolite, and because of that your total rate of reaction will be low, right, because the molecules may not go into the pore. So, there is no chance of the chemical reaction or very limited chance of chemical reaction. So, one has to look at the kinetic diameter versus pore opening in the case of molecular sieve reaction, which is true in all catalytic reaction. So, with this background, let us come to the synthesis, because once you look at these kind of definite structures, definite pore opening, a definite silicon to aluminum ratio. So, the preparation becomes a very crucial part in the zeolite synthesis, unlike your the non-zeolite materials or other catalytic material like silica, alumina, right, or ceria, zirconia. So, these type where the preparations are well known or well defined in terms of either wet impregnation, co-precipitation, sol gel method. So, these are well defined, but in the case of zeolite synthesis, the method of preparation is very important or very crucial, and it is a kind of reaction, right, a kinetic controlled reaction which is very slow reaction or ion exchange process and takes a large time and a definite temperature, because the crystals or definite shape of the framework is forming on which the further condensation takes place. So, you need a definite kind of structure when you look at these kind of a definite zeolite, right, preparation of a definite zeolite, and most of these informations are in the form of patents, right. So, all of you know that they are either calcium silicate aluminate materials, so aluminosilicates, right, or phosphorus can be imparted, right, to control the acidity in one way. So, basically either you see zeolite, aluminophosphate, right, or the mesoporous what I said, or molecular sieve material, they have one kind of process which is known as hydrothermal synthesis, right. So, that is in the presence of water and under autogeneous condition, you are just allowing the raw materials to come in contact and form a kind of gel, right. The formation of gel is very crucial, because the structure building agent which you are added and the type of gel that will decide the framework of the zeolite, right. The crystallization which takes place during this process, right, and then nucleation, crystallization. So, all this gives you the size of the crystals, right. So, that is also equally important. So, water, a large amount of water may not be good, right. Hydrothermal does not mean that you need a large amount of water, right. This may slow the process, right, it may hinder the process. So, generally the temperature required for the reaction is between 100 and 250 degrees centigrade, but again it depends on the type of zeolite, whether low temperature, high temperature, it depends on the type of silicon to aluminum ratio which is desired in the final zeolite, right. So, by having some preliminary calculations, you have to decide what silicon to aluminum ratio is desired in the framework, right, whether cation exchanger is required, whether protonation is required, or whether phosphorus is required, and to what extent. So, you have to take a definite amount of these raw materials, right, and then look at the amount of water. So, effect of water may be one process parameter, temperature may be another process parameter, time of this hydrothermal reaction or synthesis reaction is a very crucial factor, again because the gel and the nucleation from that gel is depending on the temperature versus time, right, correlation. So, just if I just look at here aluminosilicate type zeolite. So, you need a kind of silica source. So, one can take any type of silica source, right. So, carboxyl sodium silicate, which is just a glass material. So, these can be taken, right, or any other silica source, because the only definite amount of this silica is required, right, and that is for the gel formation, which is the initial reaction, right. And then you need an alumina source. So, again basically high surface area aluminum, right, or boehmite powder or aluminum oxides or some kind of solution of that can be taken, right. Some which is in the which can form the gel or which can form some complex, right, because it is a reaction between the silicate material and aluminate material, right. So, it should these two should be in the solution form, right. So, a definite solution or solvent is required to dissolve them. So, any type of these materials can be used for this purpose. Then pH is very important. Generally the basic medium is desired 10 to 12, and that again depends, because it provides the hydroxyl ion during the reaction, right. That has some important when you look at the complex which forms during the reaction, right, and the structure which builds that is a function of the pH also, right. Then template agent is very crucial, because it decides the framework and structure of the zeolite, right. The cation type organometallic complexes which forms that template is a kind of masking, right, on which the structure forms basically, right, your chemical structure or gel forms inside that, and when that this template removes, then you get that kind of framework of the zeolite, right. So, organic cations, hydrated metal ions, these can be used as a templating agent, right. Structure and framework of zeolite depends on the template. So, selection of the template is also important, right. So, you can use glycerol, you can use alcohols, right, isopropanol. So, these can also act, but there are several other type of templating agents in the form of organic cations, right. So, which can be the structure building agent for the synthesis of the zeolite. So, the process, because as I said it is a kind of ion exchange process, because right, if it is you are adding some kind of cations to the system or protons to the system, and basically it is a kinetic control, slow reaction, right, very slow reaction. You have to give enough time here in slow reaction, right. Zeolite synthesis, the reaction is stopped when thermodynamically metastable zeolite is formed. So, that is just from the thermodynamics, right. Then so you have to give enough time, the reaction is kinetically controlled, and based on that you have to just identify whether 24 hour or 7 days, sometime 20 days, right. So, because the reaction or the kind of silicate to aluminate framework which is forming depending upon the raw material, right. So, you have to look at that. So, in fact, you have to check the time to time, you have to take out your sample from that and take the XRD and then compare whether are you getting what you need, right, actually in terms of, because these should be a highly crystalline material, right. And if you do not control that, if you do not have the proper time and temperature relation or these, then you may not get a definite kind of zeolite framework. So, it may be A type zeolite, you need a Jdesm 5 or different X, Y, these can form during that, right. So, it is a kind of growth of the crystal, formation of the framework, right, and the definite kind of framework, as I said 4 membered ring, 6 membered ring, 12 membered. So, that is also equally important, right. So, it may be a some initial case, it may be hit and trial also, you have to just try at different conditions, right. So, extended reaction time at high temperature or at high pressure usually results the dense phase. So, pressure purpose is to densify the system, right, and generally it is autogeneous pressure. You have kept water, sufficient amount of water, and given the temperature, left it for say in a bath, right, and the water gets in the system vaporized, right. So, that creates the pressure inside the system, and that is why it is a hydrothermal what the word has been used. So, hydrothermal synthetic techniques, which just briefly I will talk some procedural steps of the zeolite formation, and the hydrothermal synthetic technique is basically a simple route for the formation of zeolites, right, and well known. It is the steps are well known, but only thing that how do you control the steps and to get a definite shape, and that reproducibility is a crucial step, right. And the high temperature and high pressure. So, generally more than 100 degree centigrade and pressure more than 1 atmosphere. So, which is roughly 20 atmosphere, 12 atmosphere. So, different atmosphere the reaction can be carried out. The organic inorganic materials which are used for this, right, as a templating agent, that is also equally important. So, what kind of materials should be selected, say here inorganic materials which are generally used, right, they should have super ionic conducting property, right, it is a kind. So, they should have some ionic property, chemically sensitive, right, electronically conducting solids, complex oxide ceramics of fluoride, magnetic, and these kind of properties which are desired in a final material, but the selection of the material, raw material is important when you have a different type of zeolites which I just talked here in this case. So, to have this kind of structure we need a different kind of raw material. So, that is to be selected on a priori with definite properties. So, basically when you have the high temperature and high pressure, so as I discussed basically the steps will be something like this. So, you have some kind of hydrolysis reaction, right. So, hydrolysis reaction will be when you have a added silicates and aluminates in a solution form, right, solutions of this, right, and control the pH. So, hydroxyl ions are supplied, right, and then this gives you a gel, right, gel formation. So, it is a kind of up to sol gel technique, but you have a organometallic complex, right, and in the gel because the metal particles are well dispersed. Same thing here. So, now the templating agent is required. So, gel formed on some template mask, right, and then this starts nucleation because the temperature and time and pressure. So, under this condition the small crystallites of that material, silicate aluminate material, that starts forming and that grow, right, crystal growth takes place, that nucleates grow in size, and you can add additives also at that point, right, cations if you need, right, sodium cations, calcium cations. So, additives may be added and finally, you get a crystal of that, right. The other thing, the calcination, drying, aging, these will be the second step. So, basically the first step is this, how do you get this gel, right. So, that is very crucial and that depends on the type of organic materials and the synthesis condition. So, we are just talking on that issue at present. So, need a high temperature and pressure. So, why high temperature and high pressure is required? Because the first thing I said that it is kinetically controlled. So, kinetic control reaction may need a high temperature to activate the reaction, right. So, the accelerate the reaction rate among the complex ions, because it is the raw material which you are taken, right, it is organic materials, right, and hydroxyl ions you have taken. So, there is a kind of the reaction between them, right, whatever the polymeric materials or cations you have taken, that in the presence of hydroxyl group. So, a definite pH, as I said, is desired, right. So, pH is very crucial in that way. So, the reaction rate will increase at this as you increase the temperature and make the stronger the hydroxylation reaction, right. So, it is a kind of hydroxylation reaction based on between the raw materials, right, in the presence of OH radical. This can promote the reactivity of reactants with low solubility at ambient temperature, right. So, when the temperature if the solubility is poor, right, when you have organic material and another inorganic. So, the solubility will not be good, right. So, one thing is that the pH is the decisive factor again, and the temperature may enhance the solubility of this, right. So, you need a good kind of solubility. So, the temperature is desired. Viscosity of water, that is another issue, right. So, the hydrothermal synthesis, the polymeric material which you have taken and water added. So, it is kind of some slurry type material, right, and which may be in the form of emulsion form, right. So, you need a temperature to reduce the viscosity of water. So, again temperature is desired, right. So, the mobility, if the viscosity is low, the mobility of the molecules or ions in water at high temperature will be higher, right, and that will the formation of the gel increase at these conditions. So, these are very important issues or crucial steps when the zeolite type of catalyst is prepared. So, hydrothermal conditions, that is very important, that high temperature and high pressure condition. So, water plays a very important role during hydrothermal conditions, right. So, under hydrothermal conditions water is acting as a solvent, right, viscosity has decreased because of temperature, right. Properties are enhanced one way, changing the chemical and physical properties of the reactants and the products, right. So, large amount of water is not desired, but a definite amount of water is required to create a kind of hydrothermal pressure, also pressure inside the system, right. It is the pressure which is because of the water vapor at that condition, right. So, that is also important. So, definite concentration of water is desired, and under this condition, because now the pressure increase, so the molecule will be closer, right. So, it is a kind of that the pressure may have a role from the thermodynamics also. So, it accelerates the reaction. Water also participate in the reaction in some cases, right, because water goes into the framework of the zeolite, right, XH2 which you see, right, and it also provides the pressure when you have the temperature inside the system. So, during the zeolite synthesis, the reaction is stopped when thermodynamically metastable zeolite is formed, because from the thermodynamics, right. So, the crystallization which is taking place, and when you have a high temperature time, the agglomeration may start. So, one has to control that, right. So, extended reaction time at high temperature and or high pressure usually results in a dense phase. So, that may not be desired, very high time, that is 7 days, 20 days is okay, you have to control that. You need a sufficient dense phase for the reaction, right, to have a gel and then to form a definite structure of the zeolite. But again the time is crucial. So, because I said if you go keep on increasing the time, then crystals agglomerate, right, the crystal size will increase, right. A definite crystal size is desired when you look at the surface area of the zeolite, right. So, that is important. So, most of the aluminosilicate zeolites, they are generally produced below 100 degree or just at 100 degree centigrade, because the water is to be in the gas form or vapor form in the alkaline solutions, right. So, for the low silica alumina ratio, generally the temperature is around 100 degree centigrade, but when the silica to aluminum ratio is high in the zeolite framework, the temperature should be kept high, right, 170 200 degree centigrade, right. So, in order to reduce the reaction time, especially when you have a high silicon to aluminum ratio you need in the framework, and control the crystal size, that is again important, as I said, morphology, composition, synthesis performed, that is generally done above 100 degree centigrade, because temperature high, kinetics will be high, right. So, one thing is clear, that when the silica is high in the system, then rate may be slow, right, at 100 degree centigrade. So, you need to have the temperature, right. So, higher temperature is required when the silicon to aluminum ratio is high, otherwise your time may be higher, right. So, temperature versus time plays a very important role or crucial role in the hydrothermal synthesis, right. So, the pressure is autogeneous, as I said. So, reaction is carried out in an autoclave. So, the major step involved during the zeolite synthesis or any molecular sieve synthesis is that the preparation of seed and gel mixture for the zeolite, right. So, gel formation is the one of the important. Seed is desired in some certain cases, as I said, the sodium cation, sodium, potassium, these may be added, right, to add this to the zeolite framework, gallium, right. So, whatever the or proton exchange zeolites if required. So, ammonia exchange of sodium Y zeolite. So, if the you need to replace these by ammonia cation exchanger, so ammonium type of zeolite is required, proton type of zeolite. So, that is if required for sodium Y zeolite. So, this is the second step. Then ultra stabilization of sodium Y zeolite through steaming method. So, sometimes steaming is done, right, to have a, that is the widening the pore sometime, and sometimes this also provides a kind of that is protons to the system when you have a sufficient kind of treatment with the stem. Sometimes de-illumination is required, right. So, a mild acid treatment is done to remove the aluminum from the framework of the zeolite. So, de-illumination is another part in the same step of the zeolite formation, because as I said that silicon to aluminum ratio if it is high, right. So, your concentration will be less, but strength of the acid site is more. So, sometimes you may have more loose type of acidity in the zeolite, right. So, then you need to treat with some cations, as I said, gallium may be one, right, or the you need a protonated zeolite. So, you can treat with some kind of proton acid substances, right. And to reduce the aluminum, you can do certain kind of de-illumination. So, steaming is one, but not very effective in that way for de-illumination. So, mild treatment with some EDTA, say ethyl diamine tetraacetic acid can be used, or a very dilute concentration of sulfuric acid can be used to dechelate this aluminum from the zeolite framework, but that there may be a probability of collapsing the structure when you have very strong acid taken for this de-illumination. So, proper care is to be taken while de-illumination, right. So, important synthesis parameter for a zeolite production is gel composition, that depends on the initial amount and type of the silicate and aluminate precursor, right. So, that is one. So, composition of the gel, which will depend on the hydroxyl ion also added into the system, right, during the for the reaction. Order of mixing, so type of stirrer, that is suitable kind of stirrer, right. Aging of the gel, that is time required to give the nuclear formation, right. So, you are drying that gel, right, the gel has to be ruptured, right, in the mask, inside that mask. So, that aging is important. Type of seeding material, so seeding not in all case, but in some cases seeding is required. Temperature ramp, so rate of change of temperature with time, that is again important, sudden heating, right, or slow heating, right. Reaction time, right. So, time of reaction is again important. Again the factors which affect the synthesis is chemical composition, that in terms of that batch composition, right, the batch. So, in order to get a definite silicon to aluminum ratio for a given mass of the zeolite, you have to make some preliminary calculations or primary calculation, and based on that you have to select the amount, definite amount of these raw materials, right, silicate, aluminate, hydroxyl ions, templating agent. So, all these need to be calculated before preparing the zeolite, right, and finally, you have to cross check it through different techniques, that is the analytical instrumental methods, right. So, silicon or aluminum source, so that these are very important. So, what silicon sources, silica materials, alumina materials, right. So, sources are important in terms of getting the final silicon to aluminum ratio in the zeolite framework. So, that is what you need to calculate. Alkalinity, very important, pH of the gel, right, as I said 10, 12. So, generally basic medium is kept. So, that is very important, because gel formation is related to the pH of that, right. This hydroxyl ion helps in that. Water content, that is again important, because it is a hydrothermal synthesis. So, amount of water, how much is the pressure that is required, that is very crucial for the zeolite synthesis. Inorganic cations, so these may be required. So, their amount, their type, right, concentration, organic template structure building here, right. So, this will form the structure. So, the type of that ring or type of the chain which is being used in this organic template, right, that is important. So, that will give you the final shape of the crystal or framework of the zeolite, right. Solvents, type of solvent used to dissolve these silicon, aluminum sources, right. So, these are important. Crystallization temperature and time, I have already talked. So, that is very important, we will see the effect later, and pressure, which is autogeneous pressure. So, all these are important for the synthesis purpose. So, aging, you know that aging, effect of aging on crystallization kinetics. So, it can be a separate chapter, it can, one can have the R&D in this, that what type of zeolites are desired and what happens to the structure of the zeolite after this, that is aging, right, and how the crystallization change, rate of crystallization on this aging, time of aging, right, temperature, time, and look at the growth of the crystal, right, and effect of aging on nucleation kinetics, right. So, these are important, because your final crystal size or type of the crystal, this depends on this aging, time aging, right, temperature and time. Stirring is important, seeding is important, and hydroxyl ion is necessary, as I said again, that this complexes easily with silicon and aluminum ions, right. So, the kind of complex which forms during the gel will depend on the pH, right, and so that is very important, the polymers which have been taken and at what condition this transfers or reacts, right, into the gel structure. So, this is a kind of what the soul gel type technique what you have learned before. So, just briefly the steps are here. So, precipitation of gel phase, which I talked that when the preparation of catalyst is desired. So, the gel phase is to be prepared, right. So, precipitation of gel phase. So, that will depend on the pH of the solution, right. So, you have to just control the pH, time is important and temperature is important, RPM is important, rotation speed, right, steering speed. Then dissolution of the zeolite material, the nucleation of the zeolite material which I have just shown in the steps, continued crystallization of the crystal growth of zeolite. So, this is again when the during the crystallization or nucleation formation this process will continue, right. So, that is what the time you can keep for 20 days, one can keep for 7 days, 14 days, because the crystallization continues. So, too much time may increase the size of the crystal, growth of the crystal, right. That may not be good when you have you need a nano synthesized zeolite, sometimes these are desired, right, very small particle size of zeolite which may give you the larger external surface area also, right. So, that is very important, and sometimes if you look at your methane conversion to liquid fuel, that time this nano synthesized zeolite material may be good. So, one has to look at that also, but the structure may collapse when you have a nano synthesized zeolite material, right. Then dissolution of the metastable phase, right. So, here you may add additives also, you may add seed agents also, right, to get a final zeolite phase, and nucleation of more stable or metastable phase or phases. So, that process depends on your aging time and temperature till you get a final crystal. So, in between depending upon the time you have to take out the sample and check the XRD, right. So, you have to look at the crystallinity. So, definite crystallinity, degree of crystallinity, and then you can stop or you can identify the time, right. So, this will continue depending upon the continued crystallization and crystal growth of the new phase. So, phase may transform if your time is high. So, as I said that you can have a zeolite A at one time T 1, but the same zeolite A may convert to zeolite X or Y, depends, right, because your time is different. So, because the phase is changing, right. So, when you look at a definite crystal phase, that is important. So, when I say that it is MCM 41, it means it has certain kind of definite phase also, right, or a crystal also. Same thing for the MCM 41. So, this is the difference when you have a different kind of zeolite materials, right. So, that is very important. So, crystalline phases while initial crystal, so while the initial crystal, right, are dissolved, right. So, that change, right. So, you have to identify dissolution of metastable phase, crystallization and crystal growth of the final crystallization phase. So, these all are similar stuff, but I have talked earlier also, but they depends on the aging time, temperature and the conditions of the reactant, that is hydroxyl ions inside the system, right, and you may add the cations also in between. So, this is just a typical picture. So, this is a kind of autoclave system, right, a reactor system. So, you put your samples here, all the material, raw material, silicate source, aluminate source. So, just like it is a container, right, a box, a vessel which can sustain a high pressure, right. So, because you need a high pressure which may be of the order of 50 atmosphere, 50 bar, right, and time may be 20 days, 20 days, 30 days or 1 week, 2 week, like that. Temperature may go 100 to 200 degree centigrade, which can be controlled by a temperature controller, pressure controller. So, you can have a pressure gauge in the system to control it, with safety valve is desired, right. If pressure exceeds beyond that, the safety valve should be released, used workable. So, all these kind of silicon source, titanium can be used, right, aluminum, boron, gallium, phosphorus. So, each depending upon whether you need what type of zeolite is desired, you can take these raw material or precursors of these, right. So, silicate, as I said, silica source, aluminum source, if you need some titanium into that, titanium, boron, so that can be used, gallium can be used in the framework, right. So, these oxide source, salt, oxide, hydroxide, any form of these can be used, right. So, this will be dissolved in some solution. So, solution is important, the type of solvent which is taken, right. So, depending upon the solubility you have to select them, right, the solvent, and then give sufficient time and it will make a gel, right. You have to add the templating agent, which will be amines, ammonium salt, alcohols, right. So, these can be used as a templating agent. Water is required, so water is added. So, all these things are added in this vessel and vessel is tightened, right. Close the vessel and put it in a heating bath, bomb, right. This is a kind of bomb now. So, you put it in that bath, heating bath at the given temperature and control that. So, gel will form, right, and then you may, if required, the seeding agent, you add the seeding time to time, right. You have to just look at that. You can add, when before closing this, you add all these also, right. Mineralizer if required, right. So, you add those mineral sources also. So, small concentration, sometimes acid can be H2SO4 is added, right, or some say sodium hydroxide can be added. So, these can be added here. So, finally, you will have this kind of system and you will get the synthesis of the zeolite. So, the composition of reaction mixture, right, that is gel, and the kind of precursor material used in the reaction mixture, they are very important, as I said, for the zeolite synthesis, right. They determine the property of the material, for example, morphology, particle size, distribution, homogeneity. So, all these will depend on the type of the raw material. So, this I have already discussed basically, right. So, oxide source, as I said, it can be for silica material, it can be aerosol, ludox. So, it is a kind of chemical, right, silicate chemical, right, siloxane, right, it can be precious silica material, just any silica, right, sodium, potassium, water, glass. So, glass material, it is also silica, right, fly ash will also be a source of silica. So, these kind of any silica material. So, depending upon the it can be new R&D approach also, right. So, fly ash from some say coal gasification plant can be taken, or used zeolites, say spent catalyst, nowadays plenty amount of spent catalyst comes, right. So, after some preliminary treatment, that can be reused in the process also, right. ZSM5, take the raw used spent ZSM5, just grind it and give the proper treatment, pre-treatment, and then reuse it in the process, right. So, that can be another R&D option for this. So, same thing for alumina salt also. So, any aluminum salt, so alumina hydroxides, right, alumina, sodium aluminate, or as I said again the spent alumina materials. So, with after proper treatment, because the crystal grows, the deactivation may be a problem, right. So, depending upon the type of the source or say refinery, fertilizer. So, they have the alumina as a catalyst. So, dechelate the metal part first, and whatever the used alumina left, residue left, that can be treated properly and then it can be, right. So, then you need a templating agent, because it is a structure building agent. So, any amine can be used, alkyl ammonium salts can be used, alcohols can be used, right. So, these can be used as a templating agent, sodium salts of this, right. So, these are organic materials. So, can be used as a templating agents, structure building agents. Mineralizer, sodium hydroxide, ammonium hydroxide, hydrofluoric acid, these can be used as the mineralizer. So, template is very important, as I said, because it builds the structure, right. So, the true template effect, right, where the zeolite is formed around the template molecule, right, which determines the pore topology due to its own shape. So, template has a definite structure, right. So, depending upon the structure of a template, you will get the framework of the zeolite, right. So, that is very important. The pore filling effect. So, pore size will be depending upon the type of the template which has been taken, right. So, the pore filling effect, where the template stabilize the micropores of the zeolite by filling them and thus preventing the collapse of the pores, right, because when the structure builds, let us say then the pore structure may collapse also. So, template may provide a support to that, right. So, just like a die, when you prepare the skeletons, right, and you use that some polymeric material, right, or some, and then you heat that polymer materials goes away, right, or the material goes away and then you have a structure, right. So, here also we are doing the same thing, right, a masking agent is required. So, that is a kind of mask, right. So, what type of mask you have taken, that builds the structure, right. pH stabilizing effect. So, due to the functionality of the template molecule. So, again they have some role in stabilizing the pH besides the regular hydroxyl ions. So, this is what the template structure. So, this is a you look this is the template, right, and your zeolite material goes into that, right, this, and this also acts. So, this is masking, right. So, a structure will build depending upon the type of template, right. Same thing for pore filling also. So, the material just goes inside and it fills that, right, and pH stabilization, because it provides some kind of this protons or hydroxyl ions, right. So, it can stabilize the pH also of the solution. So, all these can be used as a that the organic templates, right, they are very crucial. The selection of the type of template is important when you look at the type of the zeolite. And crystallization, as I said, is the most crucial step that is involved in the formation of the zeolite crystal, right. So, the crystallization is the crucial step in terms of the size of the crystal, which generally required for the given catalytic activity. The principal factor affecting the rate are gross composition, temperature of atmosphere and time to which it is allowed to reside in the atmosphere. So, that crystallization, as I said, is the time is important, because the crystal will grow if the temperature is high and time is high. So, it is a kind of sintering, right, growth of the crystal. So, a definite crystal size is required, right, and the concentration of hydroxyl ion on the other hand also plays a very important role, because the gel formation depends on this, right, and that gel is over which further nucleates and gives you the crystal. So, that is related to your hydroxyl ion concentration. So, this is just a picture. So, basically the zeolite formation is related to the crystallization, right, and that is the principal step in the case of zeolite formation, and this what you see the nucleate formation here. So, first is the hydrophobic hydration, right. So, that is the removal of the water, the crystal when you see the nucleate formation or crystal formation. So, it is a kind the water has to be removed, right. So, this is first, that is the hydrophobic hydration. So, first step is your hydrophobic hydration here. So, removal of the water from the crystal, right. So, that is the gel what you have, which the nucleus. Step 2 is the overlap of hydrophobic hydration spheres. So, now these are coming closer, right. So, this is a water molecule which goes. So, and so this is what. So, now they are coming closer, right. So, overlap of hydrophobic hydration of spheres, right. So, I will write here overlap. So, hydrophobic hydration spheres, right. The step 3, which is related to the templates. So, that is very important here. So, templated species here. So, templated species. So, the different kind of templates. So, see you can see here, this is the overlapping and these two overlapped, right, overlap of the hydrophobic layers, and this is a kind of structure building here, right, the templating because of the templates. And step 4, because they are now agglomerating, because the water is being removed, right. So, this is what the agglomeration. So, it increases in size, growth of crystal, right, and because of this you will have a crystal growth, right, a framework has built now, right. So, this is crystal growth, step number 5, and finally, depending upon the time which you are given and the temperature, right, the crystal continues to grow, and that is what the aggregation of the crystals, right. So, growth of the crystal by aggregation, right. So, they are just now structure is building, right, it is a kind of condensation. So, water is being removed and they are coming closer and closer, right. So, the structure building agent, that is what depending upon that. So, you have a growth of the crystal, right. So, this can be a very large crystal growth also, which may not be desired. So, you have to control these steps of this, because depending upon this step and this step and this step, you get finally this, right. That is the masking of the that is the structure builds, and the depending upon the time which you are given, the growth of the crystal will take place, nucleation will be increasing, right, or nucleation will take place. So, that is to be controlled in terms of the zeolite synthesis. So, the quaternary directing agent which I talked the templating agents, right, which just we discussed here, this one, right. So, the same thing is elaborated here, the quaternary directing agent, right, all these templating agents. So, this is what the structure. So, this is just what you look at here, it has gone inside and gave you some dimensions of that framework of the zeolite, what I was talking, right, 4.6 angstrom, a kind of cage. So, a small individual alkyl chain length quaternary directing agent, they generate the formation of microporous solids. So, amount of the carbon which is present in that ring, right, of that organic templating agent, right, or quaternary compounds which you take as a templating agents, right. So, that is important. So, this what is shown here has gone like this and the structure is built like this, right. So, this generates the formation of the microporous material if the individual alkyl chain length is small. If the individual alkyl chain length is larger, the size will be larger, because it is a kind of template on which the structure is building or framework is forming. So, same thing for this here, if you need a lamellar or 1D structure like in MCM type materials, right, MCM 41, MCM 48 what I was talking earlier, right. So, large alkyl chain length quaternary directing agents self assemble to supramolecular species which can generate the formation of mesoporous molecular sheaths, right. So, here you can see the size is between 20 and 100 angstrom, right. So, that is the selection of the templating agent or structure building agents, right. So, the kind of alkyl chain length which you select, that is important, whether it is a smaller chain length or larger chain length. So, accordingly your structure will build. So, just a typical, if you look at flow sheet form of the either it is ZSM5 or SAPO composite, simple the ZSM5 is separate prepared and then the phosphorus SAPO is to be added. So, right, a mixture of these two kind, right, combination, because you need to control the acidity in certain cases, right. So, just some say you have some alcohol group, right, structure building or this your templating agents, sodium silicate, some silicate source, some alumina source, acid, right, sulfuric acid. So, these are mixed and agitated. Then you need crystallization. So, that what we were discussing, a definite temperature is required. So, here it is around 448 degree Kelvin, right. So, temperature is higher and time is 48 hour for aging, right. So, the crystal forms, so crystallized product is here, right. Then you may add some DP amines groups, right, and then if required, because SAPO, so this is one step for just ZSM5, but if SAPO is required, so you have to add the mixture of phosphoric acid, some pseudobromide which is again a kind of aluminous powder, right, fine alumina powder, and silica solution, right. So, it may be the some tetraethyl orthosilicate or some silica in the dissolved form, right, solution form. So, this can be added during this process along with some amines, and then you mix them uniformly, again agitate it, crystallize, and you will have a composite ZSM5 SAPO11. So, it is a kind of reacted species of ZSM5 and this silico-alumina phosphate. Instead of just you have ZSM5 one, SAPO on another side and do the dry mixing, right. So, the property here, the phosphorus is attached to the ZSM5 and it is a kind of a composite material, right. So, different approaches can be used for the preparation of different kind of catalyst. So, just quickly I will go through this recipe, because we have already done the discussion on this. So, the catalyst preparation or zeolite catalyst preparation. So, basically the process is preparation of some proton type zeolites, right, which are protonated zeolites, incorporation of metallic function to them, that is replace the proton by some ammonia zeolites, gallium, right, boron, whatever, and then activation of the metal part. So, calcination is desired in that case, right. reduction may be required, then you get a complete catalyst. So, first part is just the zeolite preparation and now you metal precursor is required, right. So, that can be just like your impregnation method once the zeolite is already prepared, right, or it can be some ion exchange process, right. So, that depends on the type of the zeolite materials. So, to obtain the hydrogen form of zeolite, the ion exchange is carried out, right. Ion exchange is slow process as I said earlier also. So, you need to do repeatedly, right, 3 times 3 hours for 3 hour continuation, right, and with say just this is one method of 1 m ammonium nitrate, right, solution and temperature around 353 Kelvin followed by calcination in air at 823 Kelvin for 4 hours. So, this is one recipe, right, as I said. So, in order from zeolite material, now you need to prepare something like gallium Hz5, you have the Hz5. So, replace use the gallium on that, right, or moly Hz5, right. So, this means the molybdenum is to be attached to this zeolite frameworks, right. So, zeolites, the kinetic diameter of molybdenum and zeolite pore diameter is 1. So, whether it can diffuse into the pore or not, that is a crucial issue, right. So, it is good to replace the H positive part of that zeolite by metal species, right. So, it is a kind of ion exchange. So, ion exchange processes are very slow process, right. So, you need to give enough time, you need to give enough temperature, right, proper agitation and then you can get this type of zeolite, right. So, I stop here, I will continue quickly in the next turn.